Hi guys, welcome to today's lecture. Today we continue our discussions on simple linear regression. This is some further extension of simple linear regression. Recall that if we want to study the association between x and y, we'll limit ourselves in this class to the linear association. If the association between two quantitative variables x and y is linear, we can go ahead and use a linear function to model this association. In order to proceed, we first plot the scatter plot in order to check how large is the linear association. And then we compute the correlation. Although there is no specific rule on the cutoff values of correlation, but based on experience, the values of correlation bigger than 0.3 or less than minus 0.3 can be counted as usable correlation. And with that, we can go ahead with simple linear regression model. Now, if correlation is high enough, depending on the situation, bigger than 0.3 or less than minus 0.3, we can use a linear function in order to model the association between two variables x and y. Recall that a linear function has the following form: y is equal to a plus bx. Of course, we have y and x because these are our two variables, but we need to estimate a and b. We use a method called least squares in order to estimate a and b, and in R, we use the LM function in order to find the estimates of a and b and their corresponding p-values. After estimating a and b by running the LM function in R and checking their p-values, we go ahead and write the model. Furthermore, we check the adjusted R-square in order to see how much of variation in y, which is the dependent variable, being explained by x, which is the independent variable. The step-by-step summary of how we should run linear regression model. First of all, we have to specify our variable of interest, and importantly, we have to specify what is our y, our dependent variable, and what is our x, our independent variable. Remember guys, this is very important for us to correctly specify the dependent variable y, independent variable x, because we are either interested in studying the effect of x on y or the amount of variation in y being explained in x. Therefore, it's very important from the beginning that we should know what is x and what is y. Once we have our variables specified, we go for the test of linearity, and for that we plot the scatter plot as well as we compute the correlations. If we were satisfied with the scatter plot and correlation, in other words, if the correlation was, for example, bigger than 0.3 or less than minus 0.3, then we run the LM function in R in order to compute or estimate A and B. Once we have estimated A and B, we check their values, especially the value of B and its p-value. Furthermore, we check the adjusted R-square in order to know how much variation in y being explained. Once we are done with the values of A and B produced by the LM function, then we go ahead and write the simple linear regression model of x and y and interpret the result. For instance, we are interested in checking how much variation in working experience being explained by variation in family size, and furthermore, how is the effect of family size on working experience. First step is to specify the variables of interest. Importantly, specifying which variable is the independent variable and which one is the dependent variable. Here in this context, x is the family size independent variable, y is the working experience, the dependent variable. Second step is the test of linearity, which we do via sketching the scatter plot and calculating the correlation. Both the scatter plot and correlation show a high degree of linear association between two variables. Hence, we can model this linear association by a linear function of the form y is equal to a plus bx. For that, we have to estimate a and b. And therefore, we run the LM function, LM, summary LM, in order to compute the estimates of a and b. As you can see here, the estimate of a is 0.86 and the estimate of b is 0.338, and both p-values are significant. They are less than 0.05, and the R-square is 0.87. Hence, we can write that working experience is equal to 0.86, which is the value of A, plus 0.34, which is the value of B times family size. And from the R-square value, we know that the 87% of variation in working experience is being explained by variation in family size. And the effect of family size on working experience is of course positive because of the value of B here is 0.34 is a positive number, meaning that the larger is the family size, the higher is the working experience of the employees in this company.